In class, we simulated several population genetics experiments. We had people act as people, and we explored how different forces of evolution would affect allele frequencies over several generations. But we saw that there were several limitations to doing physical simulations for population genetics. First of all, because the class was so small, it was hard to avoid the effects of genetic drift. Additionally, we couldn't accurately show all the different forces, and we couldn't simulate very many generations because we ran out of time. So in class tomorrow, we're going to use a software program called Deme 1.0. And this software program is an Excel spreadsheet that will allow us to simulate various forces of evolution and conduct many generations of breeding so that we can get a more accurate picture of how evolution works. So this is what the spreadsheet looks like. There are two main pages that you'll be working with. The main page shows a graph of the allele frequencies. The second page, calculations, shows the actual data from one generation to the next. As you can see, Deme will calculate 50 generations of breeding instantly. We could never do this in class with a physical simulation. And the calculations will show you from each generation what the frequencies of the genotypes are, along with fitness and values of P and Q. But for the most part, you're going to be working in the main page. So let's see what this has to show us. The starting conditions show you the initial frequency of P and Q. Right now, the initial frequency of P is 0.7, but we could change that to 0.5. And you'll see that Q will change automatically because P plus Q have to add up to 1. You won't be able to change Q. All right, that's a big no-no, but you can change P in order to change Q. Now you see the 4 different forces of evolution. We have mutation rate. So if you wanted to change the rate that the A allele mutates to the B version, you could enter a number here. Now a quick note. You might be wondering why the genotypes say AA, AB, and BB. That's a little bit of a glitch with this program. Unfortunately, instead of showing a small recessive lowercase a, the program shows you a B instead. So anytime you see a B, you need to think of it as a lowercase recessive a. So this is actually the heterozygous genotype, and this is the homozygous recessive genotype. So going back to mutation, this box would let us have a mutation rate of the dominant A to the recessive A, and we could type in a number here. Now, mutation rates in the real world are very, very low, so you wouldn't want to type in something like 9, or your graph is going to be crazy. The average mutation rate for any given allele is actually 0.000000025. Very, very small. So if you're going to alter these, make sure you pick a tiny number. We can also change selection. As you can see, each of the genotypes has a number attached to it. 1 indicates that selection favors that genotype. So in this case, the homozygous dominant and the homozygous recessive genotypes are being favored. But if we were to lower these numbers, we would see different results. Immigration, another word for gene flow, shows how many of each genotype are entering the population. We can't simulate emigration directly, but you could always put in a negative number. So if you put a 5 here, that would mean that 5 individuals over a certain population size with this genotype are entering the population. Let's see what happens if we put a negative 10 in here. Again, you can see that because 10 individuals with the heterozygous genotype are leaving the population, it's changed our graph. Our final force, drift, is pretty simple to manipulate. You can either turn it on or you can turn it off. You can also change N. N is the population size. Right now we're working with a population of 2,000, but we could make it as large as 9,000. And if you flip over to the calculations tab, you'll see that now our population is 9,000. You could also simulate a bottleneck. Let's say that for a while you've got a large population, but Uh-oh, an earthquake destroys most of the population, reduces it to 1,000. Drag this all the way down. And then if you go back to the main page, you'll see that the allele frequencies have changed as a result. Finally, you have this legend. This controls what your graph actually displays. Sometimes less is more. If you just want to track what P and Q are doing, uncheck everything but P and Q. And this will allow you to see very easily what the pattern in the dominant and recessive allele frequencies are. If you're more interested in genotype frequencies, then go ahead and click the homozygous dominant, heterozygous, and homozygous recessive. And you'll see that the patterns are a little bit different because sometimes a genotype might protect a particular allele. And that, in a nutshell, is how this program works. Tomorrow in class, you're going to have a chance to manipulate all of these factors and see how they affect the trends in allele frequency. And if you check your email later today, you should see that I have emailed you this document. If you are super excited and want to get a head start in playing around with these numbers, feel free.